Okay, so thanks a lot for letting me speak first of all, and thanks for showing up. I was expecting a somewhat bigger loss of people coming from the lounge and in here, but I'm quite happy. I was not aware I was going to be filmed, so that makes me slightly nervous. But I hope I'll manage anyway. If I don't speak loud enough, please let me know. And it's really, I mean, when I say mathematical problems, it's because there are real problems in time frequency analysis and that sort of thing, where people sit down with experiments and they try to solve it, and they often do a whole lot better than mathematicians would do. However, the idea is that mathematicians like to put things into boxes and categorize and stuff like that, and find general traits between different techniques. And so there's quite a lot of problems in that regard, and that's what I'm going to be talking about. So really, it's not so much about the actual signals and how the machinery works and stuff like that, but just the math part of it. Okay, before I start, I definitely have to mention the Fourier transform. Let me see if I can roll this the other way. So I'll start by just saying what is the Fourier transform and why anyone would be interested in using it. And then we're going to build on this as we go. So the first thing is, if you have a function that is integral on the real line, what you can do is you can take that function, you can pair it with this complex oscillation or complex exponential. Let me normalize it. And then you can integrate. And you can only really say that this integral exists if the function is integrable itself. So you start by defining this, and what that tells you is somehow how much of this oscillation or this complex exponential does f have inside of it, right? So it's kind of like a regular. It's an inner product, but it's not really an inner product because this one is not L2 or anything nice like that. So it's not really an inner product, it's just a dual pairing. Anyway, that's not too important. The point is, you pair these, and it tells you how much of the frequency W here that there will be inside the function f. So if this had been an orthonormal basis, for a Hilbert space, L2 for example, this would have been just an inner product, and you would get some nice projection, but we don't have that right now. Okay, so so this is it. That's how it's defined, and what you can do is you can actually extend this, because Hilbert space theory is somewhat nicer than just the L1 theory. So what you try to do is yes, please.
What are you integrating over? Is from negative infinity?
Yes, it's from negative infinity to infinity. So this is over all reals. Okay. Yeah, absolutely. So what you want to do actually is extend this thing to L2. And so what you spend a lot of time showing is that you can actually do this. But maybe it's actually easier to say what happens when f is in L2. So what you really end up doing is you say, okay, that function is not integrable, but if I cut it off at a finite bounded interval, it will be. So what you end up doing is you say, well, let's take f, pair it again with the same thing, 2 pi I omega, and integrate it. But in this time we actually just cut it off at some bounded interval, and then we define these functions here. In this manner, for example. Okay? And the point is that it takes a while to show it, but these will actually converge in L2 norm. Okay? So this is just to get the last bit. That if you take this sequence here, it actually converges in the L2 norm, meaning that there will be a function. So we define the limit to be what we then denote the Fourier transform of that original function f right there. Okay? So this is just done, it takes a bit of preparation, but this is what you do. So that way we can move into working on Hilbert spaces instead of working on a Banach algebra. Right? Okay. So this is what we do. And then the next thing, what I'm really going to say about it, so this picks out frequencies. So this one, the Fourier transform, picks out frequencies. We can think of it as that. And so it takes out all the frequencies that there are in this f here. However, it gives you absolutely no information about what time the frequency actually takes place. And that's something we're going to address a little bit later. But think about it, the ear, what does that really do? It gets a signal in, that's my voice right now for you guys. It's just nothing but an amplitude, but you can hear the frequencies, right? You can hear if I'm very low, or if I'm speaking very high pitch, which I can't do. Something like that. You can hear that, right? And so the point is, our ear is extremely smart because it can pick it up. And it can also tell you that first I did the low sound, and then later on I did the high frequency sound, okay? But if I just take the Fourier transform, it'll just tell me that those two are there, but it won't tell me at what time they arrive. So the Fourier transform picks out frequencies, but it has absolutely no time localization. Localized. Is that a C on this? I would write it as. But it's probably a Z, right? Z. Yeah. Z, depending on which part of the world you're on. Yeah. Okay, so there's absolutely no information as to what time each frequency occurs. And so I've already mentioned, and I'll talk a little bit about what will really be the general theme for this talk is to reconstruct a function if you're just given some discrete data, discrete amount of information about the function. And so the first example that I'm going to give is for functions whose Fourier transform will actually be restricted to a bounded interval. And there's a good reason to do that, because when I speak, the only part you can hear is between some low frequency that the dogs can hear a little bit lower, and I think they can also hear a little bit higher than the highest frequency human beings can hear. So, or maybe it's only higher they can hear. But the point is that we can only hear a limited amount of frequencies. And it actually turns out that if you can only hear a limited amount of frequencies, the signal that I send out here, you can actually reconstruct the same sounds as that you receive simply by, how you say, sampling my voice at certain intervals. Okay? So you don't need to hear my whole signal, my whole voice, but my whole talk. You could actually just sit down and take a little noise that comes every, say, second or something like that, and then you could really interpolate in between those and end up getting the whole talk. Right? And this is the idea of the following example. So I will talk a little bit about band-limited functions, simply because they somewhat mimic what happens when we hear things. And this is actually, I'll say, it's quite important, because think about it, when we talk on the mobile phone, we talk and talk and talk, but the signal does not get sent as an analog signal. It actually gets sent as bit by bit digital signal. Okay? So already there we have this kind of cutting up of our voice or signal that we want to transmit. And the point is that when you receive it in the other end, you can actually get maybe not an exact copy of it, but very close to an exact copy of the signal that I put into the phone. That's when you're listening on the other end. Okay, so we're going to look at how this happens. In some sense, this is not. Again, I do not know about films too much. But let's say, let me just say that if a function in L2 has its Fourier transform, let's say, equal to 0 outside a certain specified interval. And in this case, I choose the interval conveniently so that I do not have to make too many mistakes when I do calculations. Okay? But let's just say that it's limited all the frequencies that occur in this signal, f, which is just a bunch of amplitudes, or a collection of amplitudes. If the frequencies that occur in that signal are between -0.5 and 0.5. Okay? That's just for convenience. Then we call f a half band limit. And you could of course extend this into an even larger symmetric interval. You would have to change the formulas that I'm going to give a little bit. You could also move it around and you're still going to change the formulas, but kind of the principle of this still holds true. And I'll tell you what the result is. And it's generally called the classical sampling theory, sampling theorem. But it's also known as Shannon sampling theorem. He was a guy at MIT who kind of brought it back into play and actually was one of the first people to use it in the theory of communications. But it's an old problem that actually has its roots back to Cauchy, so it's really quite old. But the result is that such a function here so if f is a half band limited, then it can be reconstructed if only you measure its values at the integers. Okay? So this is what I meant by saying that you could wait a second, measure the amplitude of my voice, wait another second, measure the amplitude, and so on. And in the end, if I was band limited within this frequency interval, you could reconstruct my whole talk. But I'm not, so you have to sample quite a lot more. Okay? But it basically says that if I measure the function at the integers, and let's also imagine we can measure in negative time. It's a little bit weird, but whenever n is some integer, positive or negative, or 0, then you can actually reconstruct the function. And what is more, there is a formula for what that reconstruction looks like. And I'll tell you why that reconstruction looks like this. The function is reconstructed by the values simply by taking the sine function and translating around according to the integer that we are measuring, and then dividing by this stuff here, and then we add it up. And of course I have to say something about, I have a sum here and it's an infinite sum, so it has to be what type of limit does this occur in. The sum both happens in L2, like the limit of the sum is both in the L2 norm, but it's also going to be pointwise. Which is quite important because you can actually reconstruct the value at a point, not just almost everywhere. Okay. But this is the point, actually these functions are all continuous, so they're almost everywhere, all of a sudden becomes everywhere. But, okay, so this is it. I'll tell you a little bit why this comes about. And this may be the only thing you see today that resembles a little bit of proof. But I'll just give the rudimentary facts. So these functions here that are half band limited end up living on the function space, or on the function space L2 from -1/2 to 1/2. And what more is, the exponentials, the complex exponentials with 2 pi I n x, or let me call it n omega, these actually form an orthonormal basis. I don't know if you're aware of this, but it really is a result in Fourier series. So the Fourier transform here is really a kind of a generalization of a thing called Fourier series, and the Fourier series actually used to go, in this case, go the opposite way and get this representation right here. Okay? So this one is an orthonormal basis. What that tells you is that f can be written, and I'm going to write the arguments of the function here as well. I'm not going to be too precise with convergences and stuff like that. But it tells you that if you take f, an inner product with these that I call En, then f can actually be expressed like this. Okay? And as it turns out, these here are exactly the Fourier transform of e to the minus 2 pi n omega. This is exactly this inner product here. And something I cheated you for, that I should have really said at the beginning, is that this Fourier transform can actually be inverted. I should have said that quite a while ago. But, well, let me say it right now. That, wait, is it okay if I change this one to a minus so I can change this to a plus? So this mapping from L2 and into L2 is invertible. And the inverse looks exactly like the Fourier transform right there. And what you end up doing is you take, I don't know how precise I should be. Let's do it with limits. And this limit is again one of those in L2 limits, right? So you get exactly the Fourier transform back, except that you pair it with this function here, e to the 2 pi r n omega. Oops, etc. So this is a general thing for all L2 functions, that you can invert the Fourier transform in this way. So what that tells you is that this is exactly the Fourier transform, or the original function evaluated at the function at the point n. Sorry. Okay. So this actually turns out to be true, and then the only thing you need to do is you need to take these here. These functions, they're supported on this interval here. So these EM really look like the indicator or the characteristic functions of that interval multiplied by e to the what's that? -2 pi I n omega. And if you want to get this function back, all you need to do is you need to take those coefficients here and let me write it up. Take the inverse Fourier transform. I don't know, maybe I should write it like this, of these EMs. Okay? And that's a hands-on calculation. That's a hands-on calculation. You can calculate it and you get exactly these functions right here. Okay? So it's just you sit down, you take these functions here, and you integrate them on the interval from negative a half to a half. And that just becomes a sine function divided by part of the argument. Okay? So this is the sine function. Okay? And this, or of course we already have this word yesterday. So this is kind of what you have to do in order to prove that this is true. And the interesting part is that you can reconstruct the function if you only know it at the integers, if it also is inside there. And not only that, it tells you exactly how to do it, and that's important. Yes.
So is the fact that our n is an integer value only because we're half band limited? So if we had like a larger band limit, our sampling would be more frequent.
Perfect, absolutely. So the larger you make this interval, absolutely, as you said, the more you have to sample. So that means if you want to capture my whole voice, you will have to sample much more often, and it'll be more expensive to actually send it.
How's the frequency of sampling related to band limit?
Well, it's directly inverse proportional.
Okay.
So
twice the band limit.
Yeah, exactly. Absolutely. So that's quite a nice feature, and it's really, you can see it by doing a change of variable. Perfect. Very good. So this is the first thing, and kind of the first success of the reconstruction issue, the whole idea of getting a function from its original value. So, yeah, so let me just stop there. Alright, the next question that you may ask, I don't know, I started at 1/4 or 20 past or something like that, so I can keep going for hours and hours. Right? Well, the next question that pops up is, that's all great, but how many of us can actually measure values of functions at just a certain amount of points? I mean, when can you say, we all know when we're doing a stop clock, like one stopwatch. I mean, there's some uncertainty related to that. So the next question is, can we do irregular sampling? And maybe what I should say a little bit over here before I move on is that what we really end up doing for these half-band limited functions is that we are saying that the norm in L2 of this sequence here, in little L2, is actually exactly the same as the norm of the function in L2 norm. Okay? That's the consequence of having an orthonormal basis, is that those two norms agree completely. Okay? And so the thing that pops in over here is, well, we don't have that situation whenever we shift, when we shift these exponentials just a little bit around, wiggle them a little bit, we're going to lose the orthogonality of these. So what we can do is maybe obtain something that's a little bit like this, but just a little bit different. And so that'll be where frames come into the picture. And maybe I should just say it the way it is. So I still am working with half-band limited functions. So I still have that. But now instead of sampling it at the integers, I might want to sample it here. Let me just call that xn minus 1. I might want to sample it here at xn. But the next one I sample at maybe a little bit closer, a little bit further, oh, xn plus 1, maybe a little bit closer, a little bit further away. But the one condition that will allow us to actually sample and reconstruct these functions is that this distance between each sample value is not too big. Okay? So if I just say that they all have to be less than delta, and I'll tell you exactly what that delta has to be. Well, I can tell you right now, the best result that there is 1. Okay, so if you sample a little bit closer than just the integers, and you are in this irregular situation, then you can reconstruct it. If you sample slower than 1 second, you're not going to be able to reconstruct it. But the result I'm going to give you is actually exactly well, it's a little bit worse than 1. It's actually going to be, what, 2 over pi. And I'll tell you why this comes in, if I have the timing right. Okay, well, but the point is, let me say, this, I think, was first, or this is the first proof that I've seen of it, is by the guy that wrote this book, which, by the way, I should say, if any of you are interested in getting through a course about this sort of stuff, and some of the open problems, like, no, some of the open problems are maybe too hard also for me. So, but if you're interested in getting into this area, maybe I could give a course about this if you're interested. So let me know, and I'll try to propose that to everyone in the main office, or at least boys. Right? But this guy this is a great book, and I'll most likely be choosing this one to teach from. But he proved this sampling theorem. If delta is less than, I'm going to write 2 divided by pi. Then, if I take these points here and the values, so what I do is, if I sample here, I take the distance between those two and I just divide it by 2. Okay? And then multiply that onto the actual sample value that is right there. This will be what is called a frame. Or another way of saying it is that if you take the little and 2 norm of this, it will be equivalent. And let me say exactly what the equivalence is. It's 1 over delta. Let me take the square here. It'll be equivalent to the norm of the function. Okay? So yeah, I get 1 plus delta, and that's not quite correct, but I'll change that a little bit. Here I actually end up getting, what, pi over 2. And here I get pi over 2. Okay? So you see now why, if I choose this here to be less than 2 over pi, I basically force this constant here to be positive, and this one is always positive, but that tells you that the function and its sample values here, with this constant in front, actually are equivalent norm. Okay? So it's not quite like having another normal basis, but it's actually enough in order to reconstruct it. And so, let me actually read this part. So it tells you that we can reconstruct the function, and I'll give you the reconstruction formula. Not by, but by inverting this operator, where we take the x minus 1, xn minus 1 over 2, and we take the values of f at xn, and we use the same function again. So we end up having this, instead of shifting by m, we shift it by the actual point where we sample. So we're going to get something like this. However, we don't get f back directly from just adding these up. We have to invert this operator, and that can take quite a while. But the point is that this is actually an invertible operator, and it can be done. And the reason that it can be done is because of this equivalence right there. Okay? And so maybe what I should say is a little bit about why is it that we can invert this function. And so I'll do a slight proof, but it's really just hand wave. Okay. I don't want to write the word proof because it's not. So let me give a small, quick argument for what is it that we really have to show in order to be able to invert that operator. Well, what it comes from is the fact that the function f is actually going to be, when it's half bandwidth, it's going to be nice and continuous, and even more, it's actually going to be have an extension, a holomorphic extension. So it's an extremely nice function. At least it's continuous. And for continuous functions, we can of course measure them. But the point is that if you take the function at the values and you just cut it up, let me maybe take. So whenever you have these 2 points, you take the midpoint between them, and let's call that yn. And when I have these 2 points, I take the midpoint between them, I call it yn plus 1. And the idea is that if you take this interval here, f inside that interval does not vary all that much. So if you do that, and you then claim that if these yns are the endpoints, these 2 functions here are actually roughly the same. Okay, and here comes the simplest thing we could have done, and we could have done this sometime after calc 1. Okay, so I'm going to use the fundamental theorem of calculus to do this one, right? The idea is that f does not change or vary much inside each of these intervals. And what is really meant by that is that if you take x to be inside this interval and you subtract the value at the sample point, well, then you can plug in, or you can really just use the fundamental theorem of calculus, right? So you take, this is going to be the absolute value of f x plus t, and t now goes from one limit to another limit. And I should really also differentiate when I use the fundamental theorem of calculus. But something like this, and we just have to put appropriate limits up here. So we could integrate from, say, in this case, it would maybe be from 0 and up to xn minus x. But we have to worry about whether this is a positive or negative number, and then we would have to swap the order of integration. But point is that you can move the absolute value inside, and then integrate with the same limit, and just keeping in mind this positive or negative nature of that one up there. But point is that if x is inside this interval, it's no more than delta halves away from the xn. Okay, because the whole distance between 2 points is less than delta, then that forces this distance to be delta halves, and this is it. So you get that if you integrate this from negative delta halves to delta halves, for sure you're going to get a bigger number. Okay. And then if you look at it, let me see. If I call this, not t because I already have that, but if I call this S of f, basically what you show is that if I take the L2 norm of this, that is exactly the same as the little L2 norm of these here. Okay? So it's a bit of a calculation, but this is how it turns out. So you have to have this, and you show that these are the same numbers. And because this one here is almost the same as f in norm. If you check out the L2 norm here, then you get the result. Okay? So, but it really relies on, whoops, on, wait, what did I say? Let me go back a little bit. This is actually the same. Wait, now I'm mixing it up. Let me see. What you really want to show is that this here, the distance from f to f itself, is actually going to be guided by the derivative here of the function. So if you take the L2 norm of this is what you get. And as far as I remember, you get a delta out of the function. So if you take the L2 norm of this function that we have right here, it turns out to be exactly this. And so you need to just employ a little thing, a little fact here is that if you have a function that's half band limited, then it'll actually be less than the size of the band limit times the function's L2 norm. Okay? So if you put all this together, and I've made quite a hash of it, but if you put all this together, you will end up getting exactly this inequality here. And this exact argument carries through, but there are some calculations that I definitely haven't done. Now, you can actually also do another step, and this is what Jorge did. He actually used the fact that these functions are holomorphic. So they have a power series expansion, and using that, and not the fundamental theorem of calculus, but using that you can actually improve on this result and get delta equal to 1 actually works. Okay? But I think I've actually said too much about this already, and I want to get into what is time frequency analysis. So let me say a little bit about that. Main point, if you sample close enough, even if it's irregular, you can reconstruct your function. You just have to invert an ugly operator, but in principle that can be done. And the way it's done is using the Neumann series. So it basically works like, I mean, we all know this formula. Where is it? We have to add from 0 and up to infinity. But this is the same as 1 over 1 minus x, right? And you can do the same thing for operators. So if you want to find the inverse of this, you take 1 minus that t, you raise it to the nth power, and you then sum it up. So you actually get the inverse simply by applying that operator minus the identity a certain number of times, actually infinite number of times. So you can invert that. I just wanted to say that. Okay. But let's get into the fun part, which is time frequency analysis. And it comes from the issue of having a Fourier transform that's not localized. So how can we localize it? Well, we could take and multiply some function onto it. So from now on, t is going to be some function that looks approximately like this. It could look something like this, or it could look, so this would be something like the Gaussian, or it could look something like just a cutoff function, like this. Okay? So something where we I don't know, want to write any functional expression for that, but those are two examples. So if we take a function like this,
is there any advantage to having a smooth function?
yes, there is, and I'm actually gonna say exactly why. I mean, the reason I want to use smooth function is that as an argument very, very similar to this one actually allows you to sample at those points. So yes, absolutely. Well, but the point is, so if we take the regular Fourier transform, it looks something like this. Well, it looks like this. So this was the regular Fourier transform, but it had absolutely no localization, time localization. However, if this function here is localized very close to 0 in time, then we could multiply that function onto it. Oops. And also translate it around. And that would actually end up giving us some information about what happens with f close to time x equal t. Right? So this object was introduced and called the short time Fourier transform. And that would be pretty much the object of what I'm going to talk about for the rest of today. Point is, you get some information about the function f, the frequencies that it contains, very close to the point t. Okay. And then after, when you are away from that, you don't get any information. Of course, there's going to be issues with this, and that's the main obstacle in this theory. But let me say, really, and then I'll address exactly your question here. If this G is smooth, I don't know how to. I need to just introduce some notation here. So I'll call this, it's not really a representation, but it is close to. So I'll use, normally people use pi for representation. So I'm just going to call this a representation, but there is some central element that doesn't show up in this version right here. But if G is smooth in both the variable t and w, depending on what that means for this representation, it'll actually mean that it'll be smooth itself, but also it'll decay pretty fast. Okay. So I'm just going to call that smooth with respect to that pi that I have up here. And it implies that it's smooth and it's rapidly decreasing, or relatively quickly decreasing, polynomial decrease. Then you can actually reconstruct that function here, if you only know it at a discrete set of points. So you only need to measure discrete time and discrete frequencies. Then you can reconstruct this function from, say, st ti comma omega. Let me say that this. So if you know these, you can reconstruct that function. And this requires again that the ti and the omega I are close enough in a very, very weak sense. Okay? But it really comes down to doing estimates with the fundamental theorem of calculus, and just instead of integrating over a line, you integrate over a square. And then there's an issue that the operation of modulation and translation, this is modulation, there's multiplication by that, they do not commute, so you need to also take care of that a little bit, but that is not bad. So you can use pretty much the same argument, and you can get your function simply from these function values. Okay. And this then also means that f can be reconstructed. So the original f that we had over here, not only the short time Fourier transform, but the actual f here, it can be reconstructed, let me say, by doing the following. You take your samples for the short time Fourier transform, and then you just let this representation act on your G. And this gives us some operator, which we also have to invert. So by inverting the T that you get from this. Now I have to think a little bit, because there most likely will be some constant here, which is on the unit circle. So because of the non-commutativity of these, I believe that you may have to multiply by some constants there. They may show up, they may not. It may just be the number one, but I forget right now. Okay. So, but you can reconstruct it and you can exactly determine what they have to be. Come to think of it, I think it is actually just has to be once the number one. Okay, so that leaves us with a few situations. Because it's cool, we have to choose these G smooth. Okay, well, let me say, when you invert this one here, what do you end up getting? You get that the inverse of that operator steps right over and works on these elements over here. So you take this sample, and then you have to take the inverse of this, acting on these pi Ti omega I of G. Okay? So it's all fine and dandy. You choose something that's nice and smooth, and you get a representation for your function f. But are these going to be nice at all? That's the question that we're going to look at a little bit here. Are these functions nice? Because you actually want, just as in the case of the sampling theorem, you want like a sinc function, or the sine divided by sine of x divided by x. You translate that around and you can get a nice, well, that's a nice function, it's smooth and everything. And in this case, very little is known about those functions here. So let me say pretty much what is known. And this is where all those open problems that I alluded to in my abstract are going to show up. Okay? So a lot of the things I'm going to say I simply not known. So what is known and what is not known? And what would I definitely like to be able to answer? First thing is, if we, and this is possible, if you sample only at what is called a lattice, so it's completely regular, you have fixed distance between all the T's you measure and fixed distance between all the W's, or at least adjacent W's you measure. So if you use something that looks like this, so you sample the short-time Fourier transform at, say, n alpha times k beta. So if you sample at those, first of all, what is needed for this to be, you need to sample close enough. And the close enough is actually hidden in these alpha and betas. So I believe that for G of x, some, like looking like the Gaussian, there has to be some constants here and some constants here in front. And I forget that right now. But if you have something that looks like a Gaussian, then you for sure need alpha and beta has to be less than or equal to 1. Okay? So that tells you that if you want to sample less frequent in time, you have to sample much more frequent in frequency. And so they have this relation that multiplied, they have to be less than 1. And it's also known with sharp less than 1 if G is any other function. But only in one direction, so that you can say that if you can sample then alpha times beta has to be less than 1 for other functions. Okay, so this is one thing that is known. But if you use those, then this operator here turns out to commute with the pi's right there. And so what we end up getting is that F can be reconstructed by these in alpha, k beta, of translates and modulates of, this is in alpha and k beta, of just one function, like this. Okay? And the point being that now you only have to invert one function. Over here you have to invert all of these. So for each sample point you're going to have a new function. Over here you actually get something nice. You only have to invert the frame operator on that one function. So that's particularly nice. And what is known is, so if G is a Schwartz function, so if it's rapidly decreasing and smooth, Schwartz, I think that's set, then so is that atom that we have right there. So this is a nice thing. You know that you can reconstruct a function simply by translating one function, and that function is very nice, rapidly decreasing and very smooth. Okay. I should mention a name. This was done by Janssen, H-A-E-M. I don't know what that stands for, but Janssen. So this is some result, I believe, from the 80s. I can't quite remember exactly when. But he showed that. How much more time do I have? I'm pretty much close to the issue, like 5 minutes. Do I have that? Okay, great. So the next thing that is known is that in order to be able to sample and a way to show that you actually do have this type of frame is to show that if G is chosen in an appropriate space, you will have a frame. And the space that is quite interesting is called the Wiener amalgam space. And it comes from amalgamating the supremum norm, essential supremum norm, and the L1 norm in the following way. So it's all the functions in, say, in infinity, for which if you take its values at, wait, this should be a smaller one, at, say, unit intervals, like this. So you take its supremums inside these unit intervals. This actually gives you an L1 sequence. Okay, so you translate those unit intervals around, and then you take the supremums, and if that gives you a summable series, summable sequence, then you have a nice function, and we call that a Wiener amalgam function. And one of my collaborators from Maryland, and he is in, I forget. Okay, it's not too important. Okudjo and Krista, they proved that if G is inside there, then so is G. Okay? And then, together with those people and a few others, we actually extended this to say the following, that if this is G, if G is in that space here, and it's also continuous, then so will the inverse. And Okay, I forgot to write the inverse operator. And nobody said anything, right? So, if you apply the inverse frame operator to this, you also get something inside that kind of nice space. And these are functions that do not have as rapid decrease as the smooth functions here, but they do actually decrease sufficiently enough that you can get nice reconstruction. I think I better stop. The question is